Hello everyone, my name is Soleha and our topic is string matching. I have Soleha, Farah and Tasbiha as my group partners. Let us introduce the problem first. So string matching informally means finding all the occurrences of a particular pattern in a text. It can be used in text editing programs, it can be used to find patterns in a huge list of DNA sequences. Formally, we define it by defining text and pattern first. So text is an array with a length of n, while pattern is another array with a length of m. And we find the pattern p of length m in the text of length n, just like shown here. We also assume that the elements of P and T are characters drawn from a finite alphabet, that is, that they belong to a finite set of characters. We also name these character arrays P and T, that is the text and pattern, and we call them strings of a character. Now let's define shifts. A shift is something that occurs in a text, not in a pattern. Shift occurs in a text and it is defined by a number. This number should be greater than or equal to 0 and should be equal to or less than n minus m. N is the length of the text while m is the text of the pattern. Is the length of the pattern. So basically, if my length of the text is 10 as shown here and my length of the pattern is 3 as shown here, then my shift should only be equal to 7 and should not go beyond that. We also need to make sure that for a valid shift, the part of the text under consideration is defined by s plus 1 and s plus m. And if that is equal to the actual pattern that we have, then we say that yes, the conditions of our shift are fulfilled and we call this a valid shift. Now let's understand it from the example right here. At s equals to 0, we look at a string of length m in text and we see if it matches the pattern that we have. The answer is no. Hence, this s equals to 0 is not a valid shift. When we move to s equals to 1, this is also not a valid shift. However, when we move to s equals to 2, so then it is a valid shift because all the letters under consideration from the text match that of the pattern, hence it is a valid shift. In a string matching problem, our goal is to find all the valid shifts in a text. This means that informally, we will be looking at all the available patterns in the given piece of text. Now let's look at the strategies and design techniques that we have figured out, and we have used two algorithms for that. These will be explained to you by my partner Farah.
The KMP algorithm constructs an LPS table, also known as longest proper prefix table, on the pattern in order to detect the pattern in the main string. What this LPS table does is help in avoiding any kind of unnecessary comparisons between the pattern and the string. We will see this through an example. Down below is given an LPS table on the pattern ABACAB. So an LPS table, or the longest proper prefix table, which is also a suffix, means that at every index I of the pattern, we save the length of the longest proper prefix, which is also a suffix. So, for example, at A, index 0, there is no such longest length of proper prefix. So we save it. As 0, save the value as 0. Then at B, we are considering the substring A and B only of this pattern, and there is no prefix, which is also a suffix. Then we look at index 2, which is ABA, like the substring is now ABA. Here we see that there is a prefix, which is also the suffix, and this is the longest prefix. Hence, the length of this prefix is A, is 1, and we save it as save the value of A as 1. Then we look at index number 3, which is C, and our substring is A, B, A, C. Here, there is no such proper prefix, which is also a suffix, hence we move on. Then we see A at index number 4, A. We again see that there is a proper prefix, which is also the suffix, and its length is 1, which is A, hence we save 1. Then at B, at index 5, we see that the longest prefix, which is also the suffix, is AB, which is of length 2, hence we save 2. Now let's see how it actually works while comparing with the actual string. Here, on the top, we have our actual string and then the pattern, and we compare one by one. We compare A with A, B with B, A with A, until we find a mismatch at index 6, which is B and A. Since we have found a mismatch, what KMP does is it looks up the LPS table value of B and moves that value minus 1. B B's LPS value is 2, so it moves to 2 minus 1, which is 1 index. Hence, it does not need to compare the 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 alphabet at index 0. It compares from index 1, which is B, and this is how we are able to avoid any unnecessary comparisons. Also, with this technique, we have seen that we only iterate on the main string once. We don't backtrack or repeat what we've already compared, and we also iterate on the pattern once in order to construct the LPS table. Hence, the complexity of this algorithm is length of the main string plus length of the pattern, which is n plus m. Then our second algorithm, which is Rabin-Karp algorithm, uses a hash function to calculate hash values of the pattern. Then it takes m size substrings of the main string and calculates hash values of those strings and compares it with the hash value of the pattern. Whenever a match of these hash values is found, then the actual pattern is compared with the substring. But it's possible that a hash value match is found, but the pattern is not found, which is known as a spurious hit. And due to this spurious hit, the worst case complexity of our algorithm is n into m. But if we have a good hash function which minimizes our spurious hits, that means whenever a hash value match is found, our pattern is also found, then our best case scenario, then our best case complexity can be n minus m plus 1.
Now let's look at the empirical analysis of both of these algorithms and see what my other group partner Tasbiha has to say about it.
We have written both the algorithms in Python and we'll be running them on the same machine. We'll use Python's time module to calculate the time taken by each of these algorithms to run. As you can see in these lines of the code, we first take the time before the algorithm has started running, and then we call the function to run the algorithm, and then we take the time after it is done running. We calculate the total time taken by the algorithm to run by calculating the difference between after time and before time. We do this for both the algorithms, and we repeat these processes several times. In fact, we repeat this 100,000 times. The reason behind repeating it so many times is so that we can arrive at a precise values for average time taken by both of these algorithms. Another thing that we are doing is that we are changing the input that each of these algorithms is receiving after some time interval. And we are doing so by taking the values from two lists that we have made, and each of these contain strings and patterns that are to be matched. After some time, we change the values by taking some value at some index from these lists. Okay, so we can run them.
Hence proved from the results gained from the empirical analysis the KMP algorithm takes a smaller amount of time than Rabin-Karp. And in conclusion, the KMP algorithm performs better than Rabin-Karp, and this has been proved by both theoretical and empirical analysis. Theoretical means that the theoretical complexity of both of these algorithms differ in a way that KMP has lower complexity as compared to Rabin-Karp, and this has also been proved by running the algorithms together and noting the time that they take to run, and hence KMP performs better than Rabin-Karp. These are the references that we used, and I hope that was helpful. Thank you.